Agricultural production is supported by four functions: soil structuration, weeds management, pest management, and plant nutrition. In order to achieve this, conventional plow-based agriculture relies on two principles of management: soil tillage and the use of chemical inputs, often associated with monocropping. Soil tillage contributes to soil structuration and, to a lesser extent, to weeds management, which is further controlled by herbicides application. Pests are primarily controlled by pesticides application and the use of more or less resistant plant genotypes. Plant nutrition mostly relies on the application of mineral nutrients under the form of chemical fertilizer and, when available, on irrigation. In these systems, the share of crop rotation is decreasing, and the choice of cultivated crops is primarily based on market opportunities and profitability. Most of the time, the straw is either exported or burnt, which leads to little restitution of biomass to the soil. Consequently, these systems are increasingly dependent on chemical inputs to compensate for soil degradation. Conservation agriculture, and more particularly direct seeding mulch-based systems, rely on three totally different principles. The first is the absence of soil tillage, or at least reduction to its minimum. The second principle is to maintain a permanent soil cover, either plant residues or standing vegetation. Maintaining this cover requires other tools for sowing that does not disturb the cover. The third principle is to rely on associations and successions of plants able to fulfill different functions. These three principles actually aim at developing the actors of the ecosystem. Plants are fundamental actors of the ecosystem. The photosynthetic activity of plants produces biomass above ground, which is then returned to the soil and constitutes the litter. The absence of soil disturbance in no-tillage conditions maintains the litter. In turn, the litter provides energetic substrate and preserves favorable temperature and moisture conditions, fostering the development of the second type of actor, which is the soil organic matter, either dead or alive. The living soil organic matter comprises the macrofauna and the microflora, which are the actors of the soil biological activity. These living organisms are in close interaction with dead organic matter, especially humus. Conditions in no-tillage systems contribute to protect the living soil community, but also the dead fraction of organic matter by reducing mineralization. Plants also have roots, and they play a fundamental role below ground. Root exudates foster soil biological activity and particularly stimulate the microflora. Plant roots and soil microorganisms improve soil chemical properties like pH, CEC, and redox potential. How are the important functions fulfilled in DMC systems? Soil structuration primarily results from aggregation processes. Soil organic matter and intense biological activity create favorable conditions for soil aggregation. Soil structure is also maintained by plant roots. Thanks to their exudates and to their physical action creating porosity. The permanent soil cover offers a protection of this structure against erosion. In turn, a good and stable soil structure enhances biological activity and deep plant rooting, which contributes to higher biomass production. Plant nutrition is primarily based on good soil structure through the whole soil profile, since it allows rooting systems to harvest a large volume of soil. The high biological activity plays a fundamental role in maintaining nutrient availability as microorganisms influence the storage, retention, mineralization, and solubilization of nutrients. In addition to the main crops, cover plants can be used for their particularly powerful rooting system able to extract and recycle nutrients from the deepest layers of soil and make them available for the main crop. These plants are called biological pumps and positively impact crop nutrition. The introduction of legume plants enables to fix atmospheric nitrogen into the soil. Thus, the different actors of the ecosystem positively influence the dynamic of nutrients, leading to higher biomass production. Weeds can be controlled by the introduction of cover crops, limiting their growth without competing with the main crop. Weed germination is also inhibited by the shade created by the litter. Soil biological activity impacts the dynamics of weed germination and contributes to reduce the weed's seed bank. Pests management relies on crop resistance, the restoration of an ecological equilibrium, and the repulsive effect of cover crops on pests. Plant resistance is naturally increased by good plant nutrition and by the activity of beneficial microorganisms. In this ideal situation, all the functions required for agricultural production are fulfilled as a result of the great number of interactions between actors. As the ecosystem functioning relies on its own actors, agricultural production can rely on a minimum of inputs. It is notably possible to give up on chemical products. Moreover, the increase in biomass production over time enables a fast turnover of organic matter. Increasing biomass production fuels the development of ecological processes, and the system becomes more efficient and independent over time. Conventional plow-based agriculture is based on the principle that one technique is directly impacting one function of the ecosystem. Consequently, technical recommendations are simple to implement and also to transfer from one place to another. However, DMC systems are based on the intensification of ecological processes. Agricultural techniques aim at fostering the number and intensity of interactions between the actors of the ecosystem. As a result, one cultivation technique does not directly impact one function of the ecosystem. Instead of this, DMC systems are based on the development of actors and their interactions to work out the fundamental functions of ecosystems. But these actors are much influenced by biotic and abiotic conditions that farmers cannot totally control. Therefore, agricultural techniques used in DMC systems must be adapted to local conditions.